Uh, Last class we have read about the paging technology, right? Paging technique, uh, which is a non-contiguous memory allocation technique. The contiguous memory allocation technique, we have three types. Contiguous memory allocation technique is a fixed number of equal number of fixed size partitions, variable size equal number of variable size partitions, and dynamic partitions. And there we have read the internal and external fragmentation. When you go for non-contiguous memory allocation, then we have first technique that we have read as the paging. The program is divided into pages, the memory is divided into frames, page size equals to frame size. Then we have a page map table which keeps track of which page is kept in which frame. Correct? And we move to a particular page, then we move inside the particular frame. From the page we get a frame number and we move inside the frame to get the required information. We have read up to this. Besides that, we have also read the free frames. We have to keep track of which of the frames are free. We have a separate three frame list, so that whenever a new page will come, it will be searched in the free frame whether any frame is available or not, so that it can be the page can be loaded into that particular frame. So we have read up to that. To implement those, we need some registers. One is page table base register, one is page table length register. Page table base register stores what? The starting address of the page table, and the page table length register stores the size of the page table. Correct? And we'll read about these TLBs. This concept you must have read in computer architecture as well. Anyway, so let us go for the TLB. Now look here, we have kept the mapping, that is which page map to which frame, in a table called page map table. Question is that where to keep this PMT? Where to keep this PMT? Ideally, the PMT must be kept inside the processor or in memory management unit, so that it will be faster for to access a particular frame, because we have to decode from which page to which frame. If that table will be there inside the MMU, which is a part of CPU, then it will be faster. But when the more number of entries are there or size is very large for the PMT, that we cannot keep inside the processor. We have a limited number of registers are there. So we cannot keep the PMT inside the processor. So where you have to keep? Another location is memory. So PMT is also being kept in the memory. Your data are kept in the memory and your PMT is also kept in the memory. However, the frequently accessed pages, the information about the frequently accessed pages can be kept inside the MMU. That memory inside the processor which stores the frequently accessed page informations is called TLB, translation look aside buffer. So what translation look aside buffer stores? The translation look aside buffer stores the frequently accessed pages information. So we have a small table kept inside the MMU, which is a part of CPU. What it stores? Page number and corresponding frame number with some control bits. Correct? So how the searching will be made? First it will search in the TLB. Either it is a hit. If it is not found, it is a miss. If it is found in TLB, we'll get the corresponding frame number. Suppose it is not found, then it will come to PMT, which is present in the memory. So from the PMT, it will definitely get the frame number. So that again, it will access the main memory for a particular information. Correct? So TLB contains only few of the page table entries. Which pages? Frequently accessed pages. The page number of the logical address is given to TLB, which searches the page number in it by comparing all entries simultaneously. So this searching is very fast. The searching in the TLB is very fast because it uses associative memory. where all locations are searched in parallel, right? So this is simultaneously all locations are being matched, compare is being done. So if the page number is found, then it is a hit. If it is not found, it is a miss. Correct? And this is the concept of the TLB. Now look over here. The processor generates the address, is called the logical address, which has two things: page number and displacement. You already know, the last class I told. This page number is searched in the TLB. There are a few entries in the table. Only frequently accessed pages are information are over here. All locations are compared at a once, whether the page number is found or not. If it is found, we'll get the corresponding frame number. Once the frame number we get, we'll use the displacement to get the physical address. Displacement means within the frame, within that frame. Correct? If it is not found, that means if it is a miss. If it is a miss, it will go to what? It will go to page map table. It will be searched in the page map table. What is miss? Miss is if the required information is not found in the TL. If it is not found in the TL, then it is called a miss. Correct? So once if it is a miss, it will go to the memory where the PMT is stored. Actually, this page table, it is being, the diagram is over here, but this PMT is inside this memory. This is inside this memory. However, this TLB is inside the CPU. So it will be searched in the PMT, the corresponding frame will be added to the displacement to get the physical memory. Is that understood? Is it understood or not? Is the diagram understood, the paging hardware? Hello?
Yes, sir.
Okay. Let us go for some of the problems, few of the problems. Suppose that 1 KB, the page size is given as 1 KB. Page size means this program is divided into pages. Each page is of 1 KB, right? What are the page number and offset of the following address references? If this is the address, what is the page number and what is the offset? As I say, page size is 1 KB. So you just divide it to 1 KB. 1 KB is how much? 1024. So 2375 divided by 1024, that gives you 2 and the remainder is your offset. Is it understood? 19366 is the address. One page is of size 1 KB. So what is the page number? So this divided by 1024. 1 KB is 1024. So divide by 1024, that will give you a page and the remainder will give you the offset. Is that clear?
Yes, sir.
Okay. So similarly, you will compute for the others. You have to compute for the others. Now look into another problem. Consider a logical address space of 64 pages. 64 page means the program is divided into 64 number of pages of 1024 words each. So every page is of 1024. So this is my program, right? My program is divided into some pages. And how many pages are there? There are 64 number of pages. And every page has 1024 number of words. Every page has 1024 of words, and there are 64 number of pages are there. Correct? And mapped into physical memory of 32 frames. So this is my memory, main memory. This main memory has how many frames? These are called the frames, right? How many frames are there? 0 to 31. So that means 32 number of 31. So 0 to 31 means 32 number of frames are there. So can you say that how many bits are there in the logical address? How many bits are there in the logical address? Total how many? This is what the CPU will refer. So therefore, this is the logical address. Correct? Actual address is this one in the memory. So this is called physical address. The actual address that you will get inside the memory is physical address. The CPU generates an address known as what? Logical address. This is the CPU generating according to this, and this is in main memory. This is in main memory. So what is the, how many bits will be there in the logical address space? Let us compute that. What is the logical address space over here? This total is the logical address space. So there are how many number of entry? There are 2 to the power 6 number of entry. There are 2 to the power 6 number of entry. What is the size of each entry? 2 to the power 10. So that gives you what? 2 to the power 16. That means the size of this is 2 to the power 16. So I require how many bits? I require only 16 bits. Is it understood? There are 2 to the power 6 number of pages. Each page is of 2 to the power 10. Therefore, size of the program is 2 to the power 16. Therefore, 16 bits is the logical address. Similarly, for physical address, how much? How many number of frames are there? 32. 32 means 2 to the power 5 number of frames. And each frame is of 2 to the power 10. How we know that it's a 2 to the power 10? Because you know that page size equals to frame size. Page size equals to frame size. So therefore, this is also 2 to the power 10. And that results in 2 to the power 15. Correct? So that means how many bits are required? 15 bits are required. Is it understood? Is it understood or not?
Yes, sir.
Okay. Let's go for one more problem. Is a logical address space of 32 pages. 32 pages, 1024 words per page. So what is the size of the program? 2 to the power 5 is the number of pages. Each page is of 2 to the power 10. So size of the program is 2 to the power 15, that we know now. So the logical address is of 15 bits. This we can compute. Now, how many bits are required for the logical address? So logical address, we require 15 bits. We require the 15 bits over here. How many bits are required for the physical address? For physical address, it says that mapped into physical memory of 16 frames. 16 is 2 to the power 4. Size of the page equals to size of the frame. Size of the page equals to size of the frame. So 2 to the power 14. So we require how many? 14 bits. We require 14 bits over here. Correct? So now look over here. This is important. One problem usually comes over here. The effective access time. How to compute the effective access time? The percentage of the time that a particular page number is found in the TLB is called the hit ratio. Right? So if M is the memory access time means amount of time it required to access some data from the memory. If M is the memory access time, A is the associative lookup. Associative lookup means which one is associative memory? TLB is associative. So to access from the TLB, this A amount of time it takes. And alpha is the hit ratio. What is hit ratio? Hit ratio is number of hit divided by total number of hits. Into 100, that is a percentage. Number of hit divided by total number of attempt. Number of hits divided. Suppose I have 100 times I am attempting, out of which 70 times I got. Then it is 70 by 100 into 100. 70%. So percentage of the time that a page number is found in the associative register. Percentage of time that a page number is found in the associative register. So ratio related to number of associative registers. Correct? Is it understood these three terms? M is the amount of time it to access from the main memory. A is the amount of time it to access from the TLB. Alpha is the heat ratio. Then the effective access time can be computed as with this formula. The formula you remember. EAT, effective access time, is M plus A into alpha plus 2M plus A into 1 minus alpha. How it is being computed? This is my main memory. This is my main memory, right? Main memory is divided into some frame. Somewhere it is being stored. This is my main memory. So CPU generates an address. What is that address? Is the logical address, correct? Where it is searched? It is first searched in the PMT. Sorry, before the PMT, first it is searched where? Before PMT, it is searched in which location? First it is searched in TLB. If it is found, it's okay, it will get the location. If it is not found, it goes to PMT from which it will access, correct? Now tell me how much time it will take. First, just look over here. So first it searches in TLB. So this amount, this time will be added or not? How much time it is? This is A. If it got over here, then it will go to memory for accessing the data. What amount of time it will take? This is M and this is A, correct? So A plus M. Are you getting me what I'm saying? This is A amount of time to access the TLB and M amount of time to access to the memory. So A plus M, if it is found in the TLB. And how many, suppose out of 100 access, 70 are found. So A plus M into for the 70% of data. So M plus A into alpha. Alpha is what? Alpha is the heat ratio. Is that understood or not? The first part, M plus A into alpha, is it understood or not? A is the access time from TLB, M is the access time from memory. So total it will take M plus A, and this will be for some percentage of data is alpha, so we multiply into alpha. If those who are not found means first it is searching with this A, it is not found, it will come to this PMT and then it will go to the memory for accessing. So A plus M, this is there, and this also added. Can you tell me what is the amount for accessing this PMT? Anyone who can say what is the time for accessing the PMT? Anyone who can say? For TLB, I know it is A plus M. For PMT, what will be this time? This time, and what is this time? Anybody one who can say? Hello? Anybody?
2M plus.
Now see over here. Where is PMT stored? PMT is stored in memory only. The PMT is stored in memory, and to access memory, I know it is M time. To access this also it is required M time. That means actually it is 2M and A time. So 2M plus A. This 2M plus A for which data? 1 minus alpha data, because for alpha it is taking M plus A. For 1 minus alpha it is taking 2M plus A. Is it understood now? Is it understood now?
No, sir. No, sir.
Just repeating it again. First, you remember that TLB may be present inside the CPU, but PMT is present inside the memory. So to access PMT, I have to access memory. To access memory, it takes M amount of time. Once I got from the PMT, what is there? The frame number is there. Once I got the frame number, I will go to that frame number to access. That means again I have to access the memory. So I am accessing the memory 2 times. One for searching the PMT. Once we got the address, again we go to the memory to that location, what address we got from PMT to access the data. So that means we are accessing PMT 2 times, along with the time lost due to unsuccessful search in TLB, that is A. Therefore, it is 2m plus A. Because the PMT is inside the memory, therefore we search in the PMT m time, we got an address and again search in another memory location m time, plus the amount lost because of searching in A. Searching TLB is A. So it becomes m plus A. So it is 2m plus A. Is it understood now? Or if any queries there, you can ask. There is no problem. If you have any doubt, you ask me. Hello.
No, sir.
Okay. Hello. I think you understood now. Now going for one problem over here, considering the TLB and PMT. Considering a paging system with a page table entry, if the memory reference takes 200 nanosecond, memory reference means to access the memory, that M is 200 nanosecond. How long does a paged memory reference take? If memory access is 200 nanosecond, how long does a paged memory reference will take? So how many times we are accessing the memory? If I don't have TLB, if I do not have TLB, how much time it will take? Here in this case, you can see over here, considering the TLB, this formula is there. So if this value are given, alpha, A, M, this value will be given. You just put the value to compute the result, right? But suppose TLB is not there. So how much time? This 2m, A time will not be there. Only 2m into the number of axes, the total number of axes. So 200 into 2, that means 400 nanosecond. Because 200 nanosecond to access the page table and 200 nanosecond to access the word in the memory. Why it is page table is inside the memory. So therefore it is 200 nanosecond. Again, it will go to the memory for accessing the word. So 200 nanosecond. This 200 for accessing the particular word means data. This 200 for accessing the PMT. Is that understood? Similarly, suppose it question is if you add associative register, that means if you go for TLB and 75% of all page table references are found in the associative register. How many? 75%. That means your alpha is 75. What is your M? M is 200. What is the effective memory access time? Assume that finding a page table entry in the associative register is 0 time. That means A equals to 0. It says that to access from the page table entry in the associative registers, that means from the TLB it is 0. So I know the value of M, I know the value of alpha, so I know the value of A, I just put it over here, M plus A into alpha plus 2M plus A into 1 minus alpha, and I will compute it to 250 nanosecond. Is it understood or any doubt? Anybody having doubt, ask me over here. Similar problems will come in your exam. Any doubt from this problem? Hello?
Yes, sir. No doubt, sir.
So for that, we may go for some protecting our memory, because the program is being stored in, in different, this is a non-contiguous memory allocation, right? So therefore, your program is now being stored in different memory, different what frames in the memory. So what we'll do, so that we have a memory protection over here. What we have done over here, we can take a page table length register to keep the size of the page table. Along with that, we'll take a bit which is associated with each for each of the entry in the PMT. For each entry in the PMT, we'll take a bit called valid bit. So if a page is valid, we'll write V, or it is set to 1. If it is invalid, we'll set it to 0. Correct? So a valid bit signifies whether a particular page is valid or invalid. Let us take an example over here. I have location from, from these two. The program can generate an address from this to this. Correct? And it is being divided into 6 number of pages: page 0, page 1, page 2, up to page number 5. Page number 5 means it is 6 number of pages. Page 0 is loaded in frame 2, page 1 is in frame number 3, page 2 in frame number 4, like that. There is no 6 and 7. So these 6 and 7 bits are marked as invalid, means these are not present currently. So that any address, if any address is referring to a particular frame, this will be show you as invalid. So any attempt to generate an address in page 6 and 7, the computer will send a trap to the operating system. Understood? So valid or invalid bit is set with the each of the pages in the page table to know that which of the page is valid and which page is not. If it is not present, currently present, so it will be invalid over there. Okay, there are some pages called the shared pages. Shared pages. One of the advantages of paging is the possibility of sharing the common code. One copy of the read-only code shared among processes. This is similar to multiple threads sharing the. So I'll just giving one example of a shared page. For example, 3 of the user are using the same MS Word. They are using the MS Word, but they are opening their own document. So you are opening 3 documents, but all are MS Word document. So it says that instead of keeping 3 copies of the MS Word, we'll keep 1 copy of the MS Word and we'll share the address with 3 different processes. Their data section will be different. Correct? So in this way, we are saving the memory. So pages, some of the pages which the page numbers which stores the MS Word will be shared among multiple processes. Correct? Just look over here. For example, I have process 1, I have process 2 and process 3. 3 processes are running. All are working with ED1, ED2 and ED3. You can see over here ED1, ED2 and ED3. Process 3 is also using ED1, ED2 and ED3. Now, as all 3 are working simultaneously, this ED1, ED2, ED3 you see over here. ED1 is stored in now this in frame number 3, ED2 is in frame number 4, and this is ED3 is stored in page number 6. 3, 4 and 6. Correct? 3, 4 and 6. So process 1 uses 3, 4, 6. So this 3, 4, 6 is over here. Can you see or not? 3, 4, 6. Process 2 is using ED 1, 2, 3. So therefore 3, 4, 6 is also given to this. The process 3 is also using this 3, 4, 6. Will also give 3, 4, 6 to process 3. But however, they have their own data. However, they have each of the process have their own set, although they all are working with MS Word, but they are working with separate files. So this file data 1 may be stored in, in frame number 1. So it is over here. The data 2 may be in frame number 7. So which is over here. The data 3 in frame number 2, which is over here. So in the page table, I will have this 3, 4, 6 is common for all the pages. For all these 3 pages, the frames are same. The only difference is in data path. So in this way, we are actually not, everyone is not keeping the duplicate copy of this, rather the same copy is being shared. So same frame numbers are being shared. Suppose the text editor is 150K. If the text editor is 150K and data space is 50, so this is how much? 200, correct? If like this 40 users are there, suppose 40, now you have taken 3, suppose 40 users are there, it would have taken this amount of memory. But if you are going for sharing, this is only once 150 will be loaded, and for the 40 users, only 50 KB will be different. So this might be requiring only 2000 KB, which is quite, quite less, as compared to the previous one. So sharing the shared pages has efficient use of the memory. Is it understood? Shared page? Is the shared page understood or not? Is the shared page understood?
Yes, sir.
Yes, sir.
Okay, the structure of the page table, memory structure of paging can get huge with straightforward method. Suppose the consider 32-bit logical address. We have 32-bit logical address. Page size is generally 4 KB. 4 KB is 2 to the power 2 into 2 to the power 10 is 2 to the power 12 bytes. So how many entries will be there? This is 2 to the 32-bit logical address space. 32 means 2 to the power 5, right? 2 to the power 5. And what is the size of page size is 4 KB. And for a modern operating system, 2 to the 32-bit means 2 to the power 32 over here. Sorry, this is 2 to the power 32. And each page is of 2 to the power 12. Each page, oh, it is written over here. Each page is of 2 to the power 12. Therefore, how many pages are there? 2 to the power 20 number of pages. So 2 to the power 20 number of entry in the PMT. Correct? 2 to the power 20 number of entry in the PMT. Correct? Suppose each entry takes 4 bytes. In the PMT, there is a frame number is also there. For each page, there is a frame number and control bits. Suppose each of these entry in the PMT takes 4 bytes. So total how many entry? 2 to the power 220 number of entry. Each entry takes 4 bytes. Each entry takes 4 bytes. So 2 to the power 2 into 2 to the power 20 is 2 to the power 22. So size of this table will be 2 to the power 22, which is very large. And storing it in the memory, continuous memory location is also difficult. Is it understood? There are 2 to the power 20 number of entry. There are 2 to the power 20 number of entries, and each entry is of 2 to the power 2. So it is 2 to the power 22 number of 22 bytes will be required. 2 to the power 22 bytes will be required, right? And this much memory is quite large, and you may not get continuous memory of 2 to the power 22. And that is the reason we'll go for hierarchical paging. We'll go for multiple number of pages. We'll go for hierarchical paging. So what we'll do, in page table, we'll break the page table. The first page table, suppose this is 1. In the page table, it is 1. That means it is actually a pointer to a location to the frame number 1. If it is 500, it goes to a 500, this pointer. That means first it will go to this PMT. There is a range of addresses to which it will go to the memory. Correct? What we will do over here? There is a set of data which is being present in the memory. The starting address of this may be kept. This is the starting address 1. So if the data is present, those informations are kept in 1. So first I will go to the outer page, from which I will get the information as frame number 1, and from 1 I will get the required information. So the break of the logical address space into multiple page tables. A simple technique is a 2-level page table. This is the example over here. 2-level paging. It is something like, when you have in your examination, what happens? You may have a notice board. A list may be given out of the exam center that roll number this to this is in hall number 3. Roll number this to this is in hall number 7. Once you reach on the hall number 5, then again it is another list you will get where roll number this is in row this, column this. So you have 2 labels. There might be 3 labels. That means if it is in multiple blocks, it is there. One computer science block, EC block, and then in the college level there will be one list where it will show, it will give that these students in computer science block. They will come to computer science, then they will get another list that from roll number, this set of roll numbers is in particular hall. Then they will go for a particular hall. There they will get another list in which row and column. So we have multiple labels are there. So if you go for 2 label, just think over here. This is a hierarchical page in a 2-level paging. What happens? This is called hierarchical paging, right? So if you go for 2-level paging, so first we go to one of the outer one. I'll get a frame number. I'll get an address. Then inside that I will again search, which gives you the displacement. Suppose, for example, logical address of 32-bit. Page size is 1K. 32-bit means 2 to the power 32 divided by how much? 1K. 1K is how much? 2 to the power 32 divided by 1K, 2 to the power 10. This gives you what? 2 to the power 22. So 22 bits are required. This gives you 2 to the power 22. That means 22 bits are required. Right? So these 22 bits are required for page number, and this 1K means 10 bits are required inside the page. Correct? Now this 22, again we'll break it. But 12 bits for page number and 10 bits for offset. So for this 22, it will use 12 bits to get over here, 10 bits for offset. Again, it will use the 10 bits to go to the displacement. So this first 12 bit, this actually first one is 22 bit. This 22 bit is nothing but from this to this. And then you need to have 10 bits for inside the page. For inside the page, it is 10 bits. Correct? This is 10 bit. This is 22 bit. Right? Where we get? From where we get this 22? With these computations. Each page is of 2 to the power 10. Total 2 to the power 32. So 2 to the power 22 number of pages. So 22 bits for page number, 10 bits for displacement. Now out of this 22, I break it again. What? 10 bit for page number and 10 bit for offset. So again, this is for 10 bit and this is for 10. So I use the first 12 bit so that I will reach over in the second level. I'll use the 10 bits over here. I'll reach a particular frame. I'll use the last 10 bits to reach on the displacement. This is called forward mapped page table. Is that understood? Two level paging. Just again dividing the page. My page length may be very large. My page length may be very large. In that case, I have to divide the page into multiple numbers. Is that understood? Any doubt over here? Hello? Any doubt in this two level paging?
No, sir.
Exactly in the same way, we may have a 3 level, 4 level, if it's a 2 level paging, so P1, P2 displacement. If it is a 3 level paging, again we'll divide it. First we'll divide into the second level, then again we'll divide into one more level. So first we'll use the P1 to reach in the second one. So we go to P2, then we go for P3 and we go for the displacement. So we have hierarchical paging or multiple level of paging over here. So 2 level may not be sufficient. We may go for a 3 level or multiple level of paging. Another one is called the hashed page table. Hashed page table. What is this hashed page table? We usually do what? The processor generates the logical address, which has page number and displacement. We search this page number in the page map table. If you could have remembered, processor generates logical address which has page number and displacement. We search this page number in the PMT. It says that instead of PMT, we have a hash table over here. We have a hash table over here. Hashing, have you read in data structure? Have you read the hashing in data structure? You must have read in hashing in algorithm as well. Hashing.
Yes, sir, we did.
So you have a hash function over here. So what we'll do, suppose page number is 23. So I'll put a hash function over here so that it will map into a particular frame. I use a hash function so that it will map to a particular frame. Maybe a reminder function or some function I'll use. Hash function, is a reminder function, is a hash function. Simplest is the reminder. You have chopping. There are many hash functions are there. So you use any hash function to reach on a particular frame. There might be a chance many of the pages may be mapping to a particular frame. In that case, I'll use a linked list. I'll use a linked list over here. So all those pages mapping to a particular frame, I'll put a linked list over here. So whenever I'm searching for a particular page, I use the same hash function, reach over here, I get a particular page, I use the displacement, then I got the physical memory. So mapping is same. Only thing is that instead of page map table, now we have a hash table. We use a hash function to get the frame number. Instead of searching sequentially in the table, we use a hash table where we use a hash function. That is the only thing in a hash page table. Correct? We have another one is called the inverted page table. Inverted page table. Very simple. Suppose, first thing is that is the page map table is for all the processes or is it separate for all the processes or only one PMT is there? Each PMT, for each of the process it will be created or for the entire operating system one PMT will be there. Any guess? I have already told also.
Sir, for entire operating system.
No, actually for every process there is a PMT. Because for every process has different number of pages. No, so therefore for every process actually one PMT is there. Now, if I have thousands of processes, then I will have 1,000 number of page map table. Again, searching the corresponding page map table will take some time. There might be small processes. Then you will have searching time will be more for finding a particular PMT. Therefore, for multiple processes, what we can do? we can keep it in a small process are there, then we merge it into one page table. So one single page table which may keep information of multiple processes, right? So rather than each process having a page table, just look over here, rather than each process having a page table, so we will not create a page table for every process, keeping track of all possible logical pages track. So instead of keeping all pages, we will have one page table over here. Now there is if I say page number 1, there might be multiple processes having page number 1. So how will you know the page number 1 for which process? So along with this page number and displacement, we'll also give the process ID. So if I say process ID 5, page number 3, displacement 10, what does it mean? So this is the page number 3, but of which process? For 5th process. If I say process number 1, page number 3, I can have same page number. Correct? So these two may be same, but the page number 3 for process ID 5, this page number 3 for process ID 1. So that can be saved inside the page table. So if you have very short processes are there, small processes are there, they may be kept, their information may be kept in one page table. Adding a process ID column, we'll add a process ID column in the page table, and processor will generate 3 things over here: process ID, page number, and displacement. That table is called inverted page table. So we have 3 entries in the logical address in the inverted page table is the process ID, page number, and offset. So first it go for the particular page number, it will find the process ID, it will go to the process ID, then it's a page number, and then it goes to the offset. This is called the inverted page table. So the problem with the paging is that difficult to share. Why it is difficult to share? Because in the sharing you have seen, it can be shared, but the program may be stored in 10 different pages. So if I want to share, I have to share all those 10 different pages. In the previous example, I have shown you ED1, 2, and 3 that is being shared by different processes. All those frames where it is being stored need to be shared. So that is a problem. And internal fragmentation at the last page of the process. I go on storing the data in the page, and the last page may not be, some location may not be filled and remain blank. So there is an internal fragmentation in the last page of the process. So this is all about the paging technique. Many important things we have covered. The next class we will go for the another important technique of segmentation. Correct? So let me take the attendance, roll number 2, 5, 10, 16, 19, 20, 21, 22, 24, 25, 27, 30, 32, 37, 39, 41, 45, 54, 61, 72, 73. Roll number 21 it is showing, so 21 will come. So the absent roll numbers are I repeat it again. Roll number 2, 5, 16, 19, 20, 22, 24, 25, 27, 30, 32, 37, 39, 41, 45, 54, 61, 72, and 73.